Okay, so we're going to take a pause from Cube for a minute, and we're going to instead look at where the speeds and capacities of roadways come from, and so let's do that. So back in the main directory cache model, I put a file called definitions for functional type, speed, cap, other things. So it's pretty much everything. So you open that up, and you might need to enable content if it has a problem. Pops up like this. So this is the volume delay curves. This is what makes it so that roads slow down. So for example, this top line is a freeway, and it means as the volume to capacity ratio gets closer and closer to 1, the speed starts going down, meaning the road's so full that cars can't move anymore. And if it starts getting overloaded, then it goes down even more. So that's what that means. So that's this file. Go to cap 1 hour 1 lane. This is how you compute capacity of roadways. And then over here is speed. Let's go to speed. So we'll talk about all of them, but first I want to talk to you about speed. So over here, this shows how you determine free flow speeds. So the first thing the model wants to know is how fast you ought to be able to go if there's no other cars on the road except for you, but the signals are still functioning as if there are other cars. So that's free flow speed, is speed when there's no other cars but there are signals. So the speed of a road is affected by several things. First is a base speed. You could think of that sort of as a speed limit, but it might actually be a little higher than the speed limit. I'm not sure how people set these, often like 5 miles, 8 miles an hour faster than the speed limit. In practice, though, we end up changing it around a little bit because of it's one of the calibration tools that we have, where you can change the speeds of the roads in order to help get your volumes correct on the base year. And then the next thing is this signals and stop density. So the number of signals there are per mile affects how fast you can travel. And the next thing is the delay. How long you have to spend each time you stop affects the free flow speed as well. So all of those are down here in this table, and my friend Ann Ho, who makes amazing websites for me, he just popped up, but I can't talk to him now. So anyway, let's see. So stops per mile. So if you look at this, we'll see if it makes sense. So on a principal arterial, this says you make 4 stops every mile, and then on collector and a local. So it's the more important the road, the fewer stops per mile. So that's what that says. That's good. And then the more intense area type you're in, also the more stops. So a central business district will have a lot more stops per mile than, say, an urbanus or a suburban area, even on the same type of road. So that's that. Unsignalized speed. So this is how fast that the road probably is in these different areas. So again, this is just guesses, and it's one of the things that makes modeling hard and makes calibrating and validating these things difficult, is the actual road speed limit of any given road is not like this. And if we had the ability to do it, we could go through and code speed limits of every road onto the network and read those speeds directly from there. But the way we did it, we just estimate these unsignalized speeds. Now this one is the uncongested delay per stop. So if the stoplight catches you and you have to stop, this is our guess at how long you're going to end up sitting there before it turns green again and you can go again. So you put all that in and shake it up, and this kind of gnarly equation is turning times into speeds, and that's what it's doing. So if you want to, you can experiment with this by, well, why don't we do that? So let's go down here, and you can get this part of the file, hit Control X, go up here, and hit Control V, and we'll put that there, and then we're just going to stretch this out a little bit so we can see everything. Alright, so I can see everything, going to delete that. Alright, so now watch what happens to these speeds. So the principal arterial in a CBD is almost 18 miles an hour. I'm going to say that if the unsignalized speed were to change to 20 because we turned it into some complete street, now it says that the actual travel speed has dropped down to almost 13 because the 20 went in right there. And then 4 signals per mile, we're going to also say that we have a lot more signals than that. So we're going to have 10 signals per mile, a signal on every block now. Now my speed is down to 8 miles an hour. And because we love pedestrians and our streets are really wide and everything, we're going to say we end up spending more time than that. This is a Salt Lake City cycle length, which is longer, and you get the delay. But you are on a principal arterial, so it's not half the cycle length, it's less than that. So if it's a 90-minute cycle length, maybe you're going to wait for 40 seconds, or a 90-second cycle length, or even 35. So now we're down to 7.2. So that's how speed works. And I'm going to save this as a different name so that you can turn it in on your own and hopefully have it be copied like mine. Okay, so going to capacity now. So that's how you determine free flow speed. The next thing you want to know is how many cars can a road carry. And this is tricky. The roads have, we measure this, or we use this in capacity per hour per lane. Then you just multiply by the number of lanes and by the number of hours in the period that you're studying to get the overall capacity of the road in a certain amount of time. So alright, so the highway capacity manual that we've spoken of before has a lot of guidance on how to analyze capacity and determine capacity, but it doesn't have that much guidance for travel models, and for which is so unusual because the travel models are what sets capacity for analysis all over the country, and I've always been frustrated about that, that they don't put more effort in. But we went through and we tried to use the highway capacity manual guidance anyway to estimate the per hour, or the capacity. So here's how the guidance says. So it says if you didn't have any signals and you could just drive with no signals, then 1,900 cars could pass over a line in an hour. And for a freeway, that number is thought of as 2,200, sometimes even 2,400 if you're measuring cars only and not trucks. But but on an arterial street, a little slower and everything, than 1,900 if it was a arterial freeway, we'll say. So then you have to start whittling that number down to what actually happens. So you'd say 1,900 could travel, but we also have trucks on the road, 1,900 passenger cars, but trucks are the equivalent of multiple passenger cars, so we factor that down by the typical number of trucks on these roads. Then bus blockage, so buses or other kinds of things that block the path sometimes. That makes a difference, especially if there's only one lane. So this is one lane, 2 lanes, and 3 lanes. So if there's only one lane each direction, then the likelihood of a bus blocking you is a little higher. Then lane utilization, this is people bunching up in one lane or the other. So sometimes even if you have 2 or 3 lanes in a single direction, it's not full capacity because everybody bunches up in one of the lanes because they've all got to make a right turn pretty soon or something like that. So that is a discounting factor as well. But the biggest discounting factor is green time. You can't, it's not a freeway. You have to let the other direction go every once in a while. So this is our guess at, if it's a principal arterial, how much green time you get. And it's not larger than that. You'd think it would be more than 50% since it's a principal arterial. And it is more than 50% of the green time, but it's not 50% of the cycle time because of the yellow and red phases. So this is green divided by cycle. So that's what that means. So 48% of the entire cycle is dedicated to the green movement for the principal arterial direction. So that's what that is. So then you go through here. Oh, and we also did an area type estimate as well. I can't remember. Well, I'm not sure what that is. Let me figure it out. Okay, I figured it out. So over here is the capacity per hour per lane. And if you look at it, it's saying, it's doing a lookup of the area type is the first thing. And then it's multiplying by all of these things. So the 1900 we start out with times all of our reduction factors and then rounded to the nearest 5 cars just to make the file look nicer. So this thing says Q47 to R51. So if I go down here to Q47 to R51, it highlighted that. And it says if the area type is 1 through 5, we're going to factor the overall capacity up or down. So the capacity then is somewhat dependent on the place that you're in. That's not part of the highway capacity manual, but we did make it a part of our model because we needed these generalizations, and we just know that the capacity is, it's a little harder to get around in a CBD. Not as many cars can do it. So that's what that is. So if you change this from a 3 to a 1, that makes it go up. So that means that the area type 1 must be rural because I have more capacity. But if I have 5, it makes it go down. So go ahead and change it to 5, and we'll leave it like that. So I have something to check in your file. Just make sure you did this part. Okay, so that's how that's working. Then over here we have this daily equivalent, and there's no such thing as a daily capacity. To take an hour's worth of capacity and multiply it by 24 creates an unbelievable amount of capacity, and roads do have an unbelievable amount of capacity if only people were willing to use it at 3 in the morning. But we want to be able to know sometimes on a daily perspective when our road is probably getting full. So what this says is oh, where's the 0.9 that it's dividing by? Divide by M4. Oh, right there, 9%. So right here I said this is how much of the volume in a single 1 hour, in the single PM hour, that's the share of the daily traffic that's occurring in 1 hour. And 8 to 10%, 11%, that's pretty typical that a single road, 10% of it's in, and 10 is a good rule of thumb, where if a road has 40,000 cars a day on it, then it probably also has about 4,000 cars in just its one busiest hour. So that's what that means. Okay, so this is my real capacity over here, but I'm divided by 0.9 and multiplied by the number of lanes that I have, in order to get a sense of what a two-lane principal arterial road can do in a single day. Okay, so that's what all these other ones do. And you might want to take a second to just study this file, maybe push pause and review it. Don't have to, but if you're curious about capacities, that's a good thing there. So then we move up in here to the freeways. The freeways are computed a little bit differently, so there's a different set of things here for them. And you can change some of these values to see what happens to the daily. So freeway higher capacity, 5 lanes. If I change that to 4, it says, oh, my 4-lane freeway, 4 lanes each direction, can probably support 186,000 cars a day. Change that to 2 and I get 109,000 cars. So 110,000 cars in one direction is what 2 lanes each direction can support. That's kind of cool, huh? So just leave that at 2 and then hit go home and hit the yellow highlighter button so I'll know you did that. And what else? Then there's a bunch of these parameters. Oh, well, this is the we also do the same adjustment. Oh, I don't know, maybe that's enough. This is already getting long. Anyway, you could play with that a little bit. Look for things that are numbers, and not sure what these charts mean exactly. I think I don't know. They're cool though. Glad somebody put those in there. I made this file originally, but somebody else added to it. Okay, so alright, so let's look at these volume delay functions. That's kind of a good thing. Okay, so this is one of the key elements of our model, and virtually all models have something akin to this as well, where they degrade the speed on any given roadway based on how many cars were on that roadway in the last iteration of the assignment, in the latest iteration. So this is what's called the standard BPR curve. Bureau of Public Roads was the agency that created this function when models were kind of first invented. And for a lot of years, this is exactly the equation that everybody used, 0.15 with an exponent of 4. But then as the years went on, lots of people started modifying that. They liked the format of the equation, but felt like they needed to modify the coefficient and the exponent to help with calibration and also to distinguish between different roadway types, because not all roadways degrade in quite the same way. It has to do with signals, and freeways that are a different animal entirely. So what I set up here, because I needed some way to see what was going on with the speeds, so I said, alright, let's take that equation there, plug it in right here. So this is that equation, and then I'll come up with a typical freeway speed, or typical speeds for these, to find a place to start my function, and then I'll just change these coefficients and exponents and see what happens. So here we are on freeway, and I'm going to change that to a 6. Let's change it. Okay, so that made a big difference. That says if you want to use a 6 in the coefficient slot here, then what it means is when the road gets to about half full, that's when things start seriously getting really bad. And by the time it's completely full, you're down to just 9 miles an hour moving, and any more than that, and it's just bad. So 6 probably is not a good number there. Let's look at what happens when I do the exponent. So if I make this into a 20, it makes it extremely steep, and that actually might be how freeways actually work most of the time for an hour. But we are doing a 3-hour assignment with our busiest with our period. So on a 3-hour average, things might be a little bit different. Anyway, so I'm going to go back to 20, and that's an interesting one. So this means when the road is about 90% full, that's when cars really are having a hard time moving. They can't change lanes very easily. They might still be moving 60, but it won't be long until they're moving a lot slower than that. And now this is where it becomes kind of a parking lot for a while. So that's how that works. So you could experiment with all of these a little bit, and you can just look over here in the chart and see the speeds changing. So that's a little bit about the volume, and this is called a volume delay function, or volume delay curves. And that's enough of this one. Oh. So go ahead and save this with the 20 in it right there, and I'll know you looked at that. And then just save the file. You don't need to put a different name on it.